Now, Professor Nenad Goveljak, University of Maribor, Slovenia, integrity of pipes by using pipe ring specimens.
Mr. Chairman, thank you very much for kind invitation to come to have presentation. I would like to say, first of all, just a few words about the man who is not with us, but who actually initiated this science topic for me and my colleagues. And this part gives me opportunity to meet also nice people among Europe from different research centers like GKSS for time. Today is Helmholtz, UN, and also from the Open, Otmar, Ipan, and others, and also many of you too. Thank you, and it's really nice to be here today. So my contribution, actually, it is joint work, which was done together with Professor Dražen Kozak from Slavonski Brod, so it is already international. He had a presentation yesterday, like introduction, but of course it is more than introduction, it is nice results, which I hope, or we hope, will be useful in the future. This is joint work with his PhD student, Dr. Damjanovic, and my PhD student, Andrej Rika. So, idea is presented already here in the first slide, that you know that we use the standard 3-point bending specimen in order to determine the fracture toughness. But this idea, how to measure the toughness of pipelines, in case when there is the notch or crack in longitudinal direction, because often the current propagates along the pipe, so you have the problem with the toughness of pipelines. And also, it is accident happened. It was happened in San Bernardino, California. Here you can see the damage what was caused by pipelines explosion in Taiwan. So many different accidents happened with pipes, and one of the reasons is that engineers need to have right fracture toughness value of this material. Also in Europe we have actually accident in Switzerland, it's called Malta, when the pipeline actually exploded for the power plant, and the reason was actually the low fracture toughness of used material. So this is why it is important. Of course, people after the testing made the analysis how and why it was happened, and they recognize that if toughness of materials will be suitable and we can calculate this value, we can use the right thickness of material. Of course, always is the question of the price. Then, in this case, we can find and make the safe pipeline structure. So, problem is with pipes that very often they want to reduce the material weight and they have the low thickness. So small thickness regarding to diameter, and in this case it's very hard to make the standard specimen from this pipeline wall. And we know and we use this different procedure for fracture toughness determination. One of this is also more than 20 years ago published GKSS P2 procedure. But also we are doing now in this all standards, trying to actually find the alternative method. Here you can see that this in axial longitudinal crack actually is rested on the pipe. So it means that for this pipe we have enough toughness that the crack is arrested and only locally is the damage. So this is actually what we want to have if this accident happened, because the damage will be small as possible. So this is here the idea which was actually patented in the Moscow, in the Russia, sorry, with the Professor Matvienko from Russian Academy of Science, also one of our collaboration workers. And actually, he also proposed that we need to do some tests in the axial direction, and then we decide to cut. And first, we start with the 4-point bending, and then we actually use 3-point bending and try to compare with the standard point bend specimen. So now I will talk more about the comparison of these results and how we can apply this. So first is how to prove that this toughness which we measured on 3-point bend specimen is the same or similar like pipe ring specimen. So on this way we use the same material. First time we cut it by spark eroding from the plate that we want to avoid the residual stresses, and then we actually made this geometry here, and we keep that this white is 2 times thickness, so similar like in standard 3-point bend specimen, and also we use this distance between pins 0.9 diameter, and also this we have the different thickness over the radius ratio. So of course the force which we applied is double because it is like 2 3-point bend specimens. But we want to actually also discover what is the difference between notched and fatigue pre-cracked pipe ring specimen. Why? Because if you are in the construction somewhere in the middle of, let's say, Russia, you have no possibility to have the servo-hydraulics machine for making a pre-crack. In this case, it will be very useful that you have the notch. And if you can measure the fracture toughness by notch, so you can get very fast results of toughness, and this can be used in calculation. So you can check the material properties which you got from the delivery. So the procedure, actually the procedure is very similar like standard procedure. We use the pipe ring specimen and 3-point bend specimen. The 3-point bend specimen we made the fatigue pre-crack from, and also we did the one group of specimen pipe ring with the fatigue pre-crack, and one group with the notches. So during the fatigue, during the testing, first, of course, we use the standard procedure for pre-cracking, that we don't avoid too large plastic zone, and also similar with the pipe ring specimen, we collect the data like crack force, crack mount opening displacement, and because we have 2 sides on the pipe ring specimen, one side we put the RMS equipment for digital image coloration, and other side we put just CTOD clip gauge. So also by RMS is possible to measure, this is influence of my let's say director of Institute GKSS from Professor Karl-Heinz Schwalbe. He actually developed delta 5 to measure the toughness, because in this case you don't need shape function. So you can measure directly toughness without that you know the shape. And we measure this by using also these delta 5 techniques. First of all, if you're using the notched specimen, pipe ring, then you have during the loading, the first step is like that, then you have the blunting, and then you have start of crack propagation. In the 3-point bend specimen, we made the Chevron notch, and also pipe rings, and then doing pre-fatigue crack front. And you can see that inside the crack goes faster during fatigue pre-crack than from the outside. And here you have quite homogeneous crack front. So this is the data about this diameter and the thickness of pipe. This is the actually the outside diameter. So by using the RMS, we make here a texture with the dots, and then the system recognizes the points. We can actually put in post-testing ANSYS 2 points to 5 millimeters, 2.5 millimeters left and right, in order to measure delta 5. And also we, on this side, use the COD measurement clip gauge. And also we have here, this point also measured by RMS scan, like crack opening, amount of displacement. So all this work actually was done in a similar way, and this is up on the triple bending test pieces, and this is here is our pipe ring specimen with the heat tinting in order to mark the crack, start of crack propagation extension. So this is also possible to measure according to standard in 9 points, so that we see what we get for initial crack length and what we have on the extension, so the final crack front, and then these results also reduce analysis. Of course, this is not standard results, so because deviations are more than 10%, and also we here measure the straight front width when we have the fatigue pre-crack in both in single edge bent specimen in order to determine the blunting line, because we want to also see if the blunting line can be used from triple bending also for pipe rings too. So here is, now you can see the notch. That's when you have the notch, this is higher actually contraction of material. Here is actually the substrate propagation, this is the final. And if you have the fatigue pre-crack, this is the actually the blunting, and then this is here is the final crack substrate propagation. So in order to have the test running by RMS, you can see here it is the loading curve. Here is these 2 points on 5 millimeters directly measured, and you can see here the crack opening during the test, and then we will have here, of course, the drop. So instability of this pipe ring with the fatigue pre-crack. So, of course, this is the last point on the curve. Then we stop the test, and we also can see measure the crack extension, and then doing the post-test analysis in order to determine the curve. Here you can see how these 2 points on the 5 millimeters displacement. Here is in the actually plan view, and here is the actually side view on this long with the equivalent strain of the crack during made by RMS analysis. So this is actually now we have the point of crack initiation. We determined this delta 5 for pipe ring specimen. It was of course 7.3 kilonewtons of force, and here you have pipe ring specimen, and also in crack initiation it's a higher, much higher force. It depends of course about the span distance, and we get also this delta 5 in crack initiation point. So we have the same material. Here you can see the correlation between the delta 5 and the CTOD, which you measured from 3-point bending specimen, but also what we do for with the pipe ring specimen. So this is one line here. In order, of course, the problem is that RMS it's not also not equipment which you can have everywhere on construction, and this is the reason why we are doing the momentum analysis in order to determine specimen-based factors that you can use with a single D, so double single D clip gauge to measure the crack opening, and then you can also calculate stress intensity, so K1. In order to do this, we make the model. We use the quarter of the specimen. It's like here, this color, and we consider two kinds of notches. One is the straight. You can see here, it's actually notch, straight fatigue front. It's not realistic, and one is a realistic uneven fatigue regret front. So why? Because we want to see what is the difference with these values, and then we can actually see if these different make this specimen useful. Also, we use the model. It is a two-stress diagram of material which we use. This material has a little so this is really transit data, and we have elastic and the elastoelastic part which we use in the armies. So you can see here, it is now the fatigue regret front, and the model was made considering the front on the left side and here on the right side. And here we use the half of the model in this case because it was not the same. And you can see also that we determine the limit load. So then we have the plasticity which comes from the crack tip to the end of this session. So if we compare now J integral values obtained by a standard, like let's say standard admissibility, and the final element modeling, we have quite good and quite similar agreement in these two for J values. And this is now model with the only notched specimen. So we now compare our test and our final element results. This is the blue line, final element modeling, and the experiment is the red line. So we consider this real fatigue regret front, and just the start the loading up to let's say maximum displacement, and then we actually take this value of force. So we have quite good correlation between the two values. Also, you can see correlation between the comparison for the base method made on the standard specimen. Also, we have here instability, so a quite good agreement. We use the same mesh elements and same density of mesh elements too. So here we want to compare the notch and fatigue regret front. This is the blue line, and this is the average. So we can see that for the same average crack length, here we get quite good agreement between this result. That means that really it's possible to use the notch specimen in this case, specimen for the testing. So here we have the results of C2DR curves. Here are made by data 5. This is actually the blunting line and formula is used, which is in the standard data set procedure 2. So we have the crack initiation area from these different specimens, and also we did the same with the same blunting. And we have also crack initiation. So we can see the difference. That here is the single H non-bending, and here is the piping specimen crack initiation, double crack initiation. So it's almost the same range, even to get some higher values of C2D. So now we can say that that C2D can be obtained directly by measurement C2D delta 5, and as I said, by using the RMS by DC or some digital image variation measurement system. And also we see that we have the quite similar curves and also in quite near area crack initiation. So this this is also we got a quite good relation between experimental and numerical results. Therefore, we can actually try to now determine stress intensity factor, because this is what we need in the practice, that engineers can put into some parameters and easy calculate. So we did this. Of course, now we use the straight line of the graph because it's like universal, so everybody can repeat and check. And then also we compare with this what we have on the specimen with a decrease back from. And we tried here, we use like solution like the highest stress intensity factor which we get in the crack initiation, start initiation point here. So it is only used for this line, in the beginning of the line, as crack initiation is relative fracture toughness parameter. So here is the formula which is used for stress intensity factor for three-point bending specimen is similar, and also we use here similar formula, but we only want to change this shape function and compare this shape function in both cases. So here we have this is example with the difference between Arati and the thickness 5 with the crack notch, actually notch 0.5 of width, so crack ratio, and we put here in fraction 0.175 millimeters. You can see for this model what is actually from this stress that we got on the surface, and also what outside stress and what is in here in this section. So also in this case, of course, we got quite, let's say, symmetric distribution of stress intensity factor. Of course, the highest value is in the middle. So now, here is the outside, and here is the inside area. So here, we use this formula for F star, which you can see here. So these values actually can be compared now with the shape function of pattern specimen. And what we did, we calculated the stress intensity factor in this point and put here for different R over V ratio. So R is output diameter. And this is one line. This line belongs to 0.45, belongs to 0.5, and this green dot is 0.55 like that. So here we have around 8. With the difference between R and V, we have like small drop. So this is now still in progress investigation. We are assuming, of course, reaxiality problem and plane strength conditions too. So, but we are going also to discover this in the future. So this function now, looking like that, you can see that the difference between the fibrin specimen intensity factor and three-point bending is between 0.8 to 0.12 or less than 30. So it is, let's say, about 5 to 6% difference between fibrin specimen and this. So actually, the toughness which you are got from the fibrin testing is quite similar with this, the same material which you got from the bending specimen. So if you now use for this different spectra of ratio between diameter and thickness, you can put this, of course, in this formula, and then you can calculate with the given ratio and given depth what is the stress intensity factor values. When you put here these all values, it's of course quite simple line. Now, because this is just in 3D how it looks like this intensity factor distribution regarding the crack depth from 0.45 to 0.55, and here from different R ratio from 5 to 10. So, how to apply this in the structure? It's actually easy. You need, of course, to have a tensile test to do, and you need to cut the ring. Ring should be the double of the thickness of the wall, and then you can make the notch, and then the test that you should recognize the amount of displacement, and when you got this curve, by applying these stress intensity factor values, and also you can get the point values along the extension. If you, for example, doing multi-specimen methods with different extensions, and you can put the line and tentatively estimate the stress intensity factor. So, in conclusion, sorry for this question. In conclusion, I can say that in case when standard specimen is not possible to use, you can use the pipe specimen, cut from the pipe, one only small piece. It's very cheap, actually not costly, and we can also, we have no possibility to measure the delta pipe by using RMS. Then we can use also this stress intensity factor solution, and then go to still different crack extension because the J archer or the archer for the fraction. Thank you very much for your attention.
Thank you.
To je bila